All right, good morning, everyone. We're a minute late, but we'll call it good anyways. I wanted to welcome everyone to LPKF Studios here in Portland, Oregon. Today we're broadcasting live our newest webinar, Laser Welding of Transparent Plastics. Now this is clear-to-clear polymer bonding with high wavelength lasers. My name is Shane. I'm in the marketing department here at LPKF, and I'm joined today by Josh Brown, Laser Plastic Welding Sales Associate here at LPKF, and a special guest today, Dr. Tony Holt. Now, he's a West Coast General Manager at IPG Photonics. Now, he's run a lot of applications related to this and actually did a lot of the early work on transparent laser plastic welding. If you have any questions throughout today's webinar, feel free to submit them whenever you want. You have a go-to webinar questions panel. You can submit them there, or you can submit your questions via Twitter. Our account is at LPKF_USA, or you can do this by tweeting your question with the hashtag #LPKF. We'll be covering 6 topics throughout today's presentation to give you the full overview of what this new technology is. And the very first we're going to start with is, what is laser welding of transparent plastics? So Josh, why don't you take it away from here?
Thank you very much, Shane. Hi everybody, Josh Brown here. And Tony, I believe you are now unmuted, so how are you doing down there in California?
Yes, indeed. Good morning, everybody.
So we'll keep this pretty conversational if we can. Tony, if you feel like you want to add something, feel free to chime in whenever. And as Shane said, ask your questions throughout the webinar. We may or may not be able to stop and answer a few of them as we go. If we don't get to it, then we'll cover them at the end. So hopefully we'll go for about 30 or 40 minutes here and then cover questions right after that. So that being said, let's jump into topic number 1. So what is laser welding of transparent plastics? So essentially we're talking about bonding 2 clear pieces of plastic, but the real key here is we're going to do it without additives. So in a second here, I'll compare the regular through transmission laser welding, or the laser welding you've most likely heard of in the past, with this new form of laser welding that we're talking about today. So you might also hear us refer to this form of laser welding as 2-micron welding. That has to do with the wavelength of the laser. It's a higher wavelength. Or you could hear us refer to it as laser welding of transparent plastics. So there's a few names going around, just industry lingo, as this new technology kind of finds its traction in the industry. So in comparison, again, today we're talking about LWTP. In the past, though, you may have heard of through transmission laser welding. So the real difference is in the wavelength of the lasers. As you can see, the through transmission laser welding, we're typically dealing with near IR lasers between 800 nanometers and 1064. As we get into this new type of laser welding of transparent plastics, we're looking at higher wavelength lasers, sometimes double the wavelength, up to 1500 nanometers through to 2000 nanometers. So again, 2000 nanometers, that's 2 micron. And that's the correlation. That's where you'll hear us say 2 micron. You might hear Tony say fiber lasers. That's what we're talking about. It's all the same. Again, the big difference here is that we're doing this without absorbers. So let's talk a little bit about why this can happen and the difference between the through transmission laser welding or the original type. So essentially, here's a pretty standard pattern of absorption. This is a pretty common thermoplastic. It's a polycarbonate. So again, this is a polycarbonate in its natural state. So if you're familiar with polycarbonate, it's a very clear, very optically clear piece of plastic. On the left here, we have the percentage of the laser radiation that's going to be transmitted. And then along the bottom, we have the wavelength of the laser that we're talking about. So regular through transmission laser welding, we're typically dealing with lasers in the wavelengths of 800 nanometers to about 1064. So anything under about 1500 nanometers, and you're seeing most of the laser radiation is going to be passed straight through the plastic. So if you shine a laser on it, the majority of that radiation is going to go straight through it. What we're dealing with What we're talking about today, however, is we're looking for a little bit more inherent absorption of the laser. So again, the plastic is still in its natural state, but we want to have the ability to absorb some of that laser radiation into the plastic. So once you get up above 1500 nanometers, the laser wavelength starts to react differently to the thermoplastic. And so what we have is this, these peaks here and then this small valley. But what we're really getting at is between about 1700 and around 2000, we have what I like to kind of refer to as the Goldilocks zone. It's where we can get some of the laser energy to pass through and some of it to absorb. It's about 50-50, not quite. In this case, we're not absorbing too much of the laser energy that we can't still pass it through to the lower layer, but we're absorbing just enough to get volumetric heating through the plastic. So here's kind of a cross-section of what it would look like. Again, we have the right balance here of absorption and transmission. So we can pass the laser through one piece and you're still going to see laser radiation make it through to this lower layer. But that being said, we're getting volumetric heating throughout the parts. There's also what you could kind of not so technically refer to as a lensing effect. This happens with all lasers. Anytime a laser is passed through a lens, whether it's a glass lens for your optics and focal control, or whether the lens is a piece of plastic, you're going to see some inherent absorption of the laser at a surface of, of each surface of the lens. So what tends to happen is because we have two surfaces here in the middle, there's a phenomenon where the majority of the laser energy tends to stay at the interface of the two pieces of plastic, which is fantastic for welding purposes because that's exactly where we want the energy. So what do you need in order to make this happen? Well, like we mentioned before, we need a laser with wavelengths greater than 1500 nanometers. Typically, and Tony will attest to this, we're going to see lasers more around the range of 1900 nanometers. That being said, you saw the chart. We can play with wavelengths. Anything up above 1500 though, and we're going to get the absorption that we need to weld plastics without additives. Also, we need the two or more clear pieces of plastic. The reason I say or more is because we have the option to bond more than one layer with this method. Again, you'll see some pretty cool pictures, especially one that Tony's done down at IPG. I'll let him talk about that though. Now, I want to clarify something. When I say clear, I might say clear, I might say natural, I might say translucent or transparent. Any of those will work. Most thermoplastics in their natural state are going to be clear or translucent, but there are some plastics like PBTs or nylons that even in their natural state they're going to have kind of a milky or cloudy color. That still applies to the technology we're talking about today. That means the plastics don't have to be perfectly clear, just in their natural state. We also need clamping force and then material compatibility. So if we're welding two dissimilar pieces of plastic, then we need to have the melt temperatures of the two pieces of plastic need to overlap somewhat. They also need to have similar surface energies and similar chemical makeups. I'm going to jump ahead a slide real quick here. If you're not a polymer expert like I know I'm not, then we do have kind of these cheat sheets for letting you know which types of plastics are going to weld together. Keep in mind this material chart was actually created for regular through transmission laser welding. However, for the most part, these are all going to apply because really what we need is just similar material compatibility.
Can I comment briefly?
Yeah, absolutely, Tony.
Josh. Yeah. What we have found is that sometimes you can bend these rules a little bit because you have the volumetric absorption, because you can create rather more mixing than you can with the through transmission laser welding. We have found that although your rules are generally very, very true, in some instances we can tweak those rules just a little bit because of the enhanced degree of mixing. It's not always possible, but in some special circumstances it might be.
Yeah, that makes sense. Thanks, Tony.
Okay.
Absolutely. So let me jump back. We're controlling the laser beam with two galvo scanning mirrors for the most part. This is how Tony would be doing it in his lab down in California, and this is how we would do it in the lab we have set up at our German headquarters in Erlangen. but basically the laser beam is going to be controlled with a galvo scanning mirror, so we can set up contours in software. The software will push the information to a PLC, which will then control the mirrors, and we can drive the beam in an XY motion pretty flexibly. So typical travel speeds, we're seeing 20 to 80 millimeters per second as working travel speeds, but different than through transmission laser welding, where a lot of times we're making multiple passes. Here we're usually making a single pass, maybe 2, 3 at the most. Tony, you might have different experience with this, but for the most part we're seeing a single pass can usually handle what we're looking for. So even though that the travel speed might be slightly slower than regular through transmission laser welding, because we're only making 1 or 2 passes, it's still a very fast process and absolutely adequate for production.
Yeah, you're quite right. It is material dependent to a certain extent. Sometimes 1 pass is fine. Other times you might need to heat it up rather more slowly with 2 or even 3 passes.
Yep. So why is this a big deal? Why are we even talking about this today? And what are the influences going to be for you guys, for the industry, etc.? So really the big difference here is that we can now weld plastics without any absorbers. And so when I say absorbers, I'm talking about whether that's an absorber like clear weld that allows the plastic to remain clear, or if you're talking about adding pigmentations like carbon black to the lower layer. If you're familiar with regular through transmission laser welding, commonly the lower layer had to be black or of a darker color. That would allow for the laser to be absorbed into that part. That being said, we don't have to have that anymore. Now we can weld 2 plastics without these absorbers. So this opens up possibilities for new joint entry, new joint designs, and then also obviously for color combinations. So and then beyond that, we can do multi-layer applications with films. And it doesn't even have to be films. We've done hard to soft. We can do hard to soft to hard, and you'll see a few examples of that here in a minute. Just really quickly too, the laser welding family, which laser welding of transparent plastics, LWTP or 2 micron, like you've heard us say, that all falls under the laser welding family. Those all share these lower advantages. So particulate free, it's great for clean room environments. Localized heat, we're really only applying heat where it needs to be. We can do this very precisely. Opposed to ultrasonic welding or vibration welding, we're not going to be stressing the parts too much. And then just on down the list, there's a lot of advantages to laser plastic welding, and those all still apply with LWTP laser welding as well. So the big deal about no absorbers, one, specialized absorbers, they can be very expensive. Obviously, if you dope them into the plastic, they're going to be more expensive, but if you apply them locally at the joint, which we see a lot in production before this technology existed, it's difficult to apply and it can cost a lot to figure out how to do that. So now that we don't require these absorbers anymore, the costs of welding 2 clear pieces of plastic is it's going to be significantly cheaper. And then also on top of that, even though these absorbers were they allowed the plastic to remain clear, they still had some effect. You would see this greening effect of the plastic. It wasn't completely clear. So, but I think for the medical industry and the biotech industry, the big one is going to be the FDA certification process. No longer will you have to push through another additive or another material to the FDA. Now you're just saying, hey, look, we're welding 2 pieces of clear polycarbonate together. We're not adding some obscure special chemical that no one's ever heard of that has to go through this process. So this is huge from a standpoint of simplifying the certification process as you pass medical devices into the FDA certification program. Kind of leads us into my next, the 3rd topic here, which is industries. The big ones that we see are medical, biotech, and consumer. That being said, there's going to be applications outside of these as well, but the one that we're really excited about is medical, and then obviously kind of biotech is a subset there. But you'll see applications like microfluidic devices, as you can see here on the bottom. Very small channels require precise welds. Well, we can do this now, again, without having to add any specialized absorbers. Catheters and tubing. situations. Tony's even been playing around with welding, making butt welds, which is a pretty important improvement, and we'll talk about that a little bit later too. And then bags and connectors. And then you see the biotech in regards to that, flasks and cell cultures. So in consumer, we feel like it'll catch up eventually. There's a lot of potential here, mostly for aesthetics and design elements, playing with different color combinations, allowing us new joint entries, etc. So notable materials. So we're going to kind of jump into the materials section and applications. I might go back and forth a little bit, but notable materials for LWTP, and again, this is not all of them. These are just kind of the ones that we've seen have the most traction so far. And again, a lot of these you see in the medical industry. So polycarbonates, acrylics, COPs, COCs, and then obviously flexible materials like TPUs and TPEs. We're seeing happen a lot of applications with those. I should have also included polycarbonate on here, but the reason these materials are notable, in my opinion, is their high optical clarity. Like I said before, we can weld all thermoplastics in their natural state with this method, but it's the high optical clarity plastics that are really gaining traction. This is where all the curiosity is so far in the industry, and that's because with this method, we're not limited to adding colors anymore. We can weld clear plastics. So if you are looking to have a nice clear part, we can do that, and it's still going to be clear when we're done welding it. Tony, have you ever seen any, I mean, if you had plastics to add to this list as far as popular plastics?
No, I think you've pretty much covered the main groups there. I think obviously as the polymers become co-polymerized, there's many different mixtures of polymers, and there are requirements to substitute for PVC and for polycarbonate. We're seeing lots of blends of different polymers that are all really quite weldable as well, apart from the basic groups that you have on the list there, Josh.
Okay, good. I'm glad we got most of them covered. We've seen a few applications come through with COP and COC. If you're in the medical industry, you've probably heard there's kind of a lot of curiosity going around with these plastics for replacing PVCs. They have a lot of the same characteristics as PVC, but they don't come with, I believe it's the DEHP, which is considered a carcinogen. So this is a huge breakthrough, and we're seeing a lot of success welding these, multiple applications so far. So that's definitely another fun and exciting new avenue that we've seen with LWTP. So let's jump into a few applications, and these are just different material combinations that we've put together. So a lot of these we're really just testing. Some of these took place in our lab in Germany, and then Tony, I'll have a few slides here at the end to show you with some applications and materials that he's welded in his lab down in Santa Clara. So in this case, we have just 2 PMMA foils, pretty thin, 250 micron thickness, and I have a little animation here if it wants to go for me. So again, you just get that volumetric heating through the part. So the weld zone's actually taking place throughout both pieces of plastic. Again, multi-layer and foil stack-ups. So in this case, we had 4 polyurethane foils. We actually have a couple more exciting slides here, but I'll let Tony talk about those ones. But we've done 4. I think we've done a few more than 4 in our lab, but in this particular instance, it's just proving the concept that we can weld multiple layers. Here's one where we have PC foil, so a relatively flexible foil with 2 PMMA sheets above and below it. So all different thicknesses, and these are all weldable together. Again, the volumetric heating effect that you see with this type of laser welding. You can see a scaled up view of that, nice, very clean weld seams. It looks really good. You can't tell a huge difference between the clarity of the seam and the plastic itself. So again, aesthetically, it's a very pleasing weld seam. COC foil, like I mentioned, these are gaining a lot of traction. 150 micron thickness, and this is actually a microfluidic sheet, which this opens up another realm of possibilities for microfluidics. Essentially what's happened here is the lower sheet, the COC, You can see down here this has channels basically etched into it, and then the COC foil is laid on top of it. And what's happening is as the weld is taking place, you're left with these reliefs or these channels. And it does a very nice job of this. That's because the laser doesn't necessarily have to travel perfectly on the outside of the channel. We can actually overlap it a little bit, and you still have this nice clean edge where the channel takes place because we don't have any absorption at that point. So it works out very well for microfluidics and very fine microfluidic devices. Here's another example of that. This one is a thickness of 1 millimeter, so we're slightly thicker here, and you can see just the nice clean channel edges, and again you maintain the high optical clarity. This particular slide, I want to show the difference between, again, what I was talking about between clear plastics, translucent plastics, transparent plastics. So they can all be welded. In this case, we have a translucent PC sheet, so it's a little bit foggy, but absolutely weldable with TLPW. And then in this case, we have a high transparency PC sheet. So again, as long as it's a natural thermoplastic, it doesn't matter if it's translucent or transparent, we can weld them. This is showing actually an instance where we did a pull test, so on that high transparency PC. So you see the material breakout in the weld seam. This is good news. That means we created a bond in the polycarbonate where it's not just a surface tacking. The two pieces of plastic actually fuse together, and as we pulled them apart, you see all the cracking and the micro fractures, and that lets us know that we've actually fused the two parts together. This is actually a test that we ran. Tony, I believe you guys ran this one in your lab, but what we're looking at here is a clear to black, and why this is interesting is because that lower black layer, although it is black, it is actually transmissive to the laser. So any laser you shine on this black part would pass right through it, except for the higher wavelength lasers will get some absorption. It's dyed black rather than filled with carbon pigment, and that allows laser to pass through it. This being said, with the 2-micron technology, what we're able to do now is we could theoretically bring the laser in, and I believe we did this in this case, we could bring the laser in from the black side and still weld these plastics together. So the laser would be passing from the black through to the clear. This opens up possibilities. We've had a few requests for this, or at least just more information for automotive lighting, where you're limited on the colors of plastics that you're trying to weld together. And so again, this is what I was talking about as far as color combinations and joint designs. We're opening up a lot of opportunities for how we can approach these now. So Tony, that brings me to you. I think you got a few slides here, so I'll just kind of let you take the reins.
Okay, I just wanted to point out that we manufacture the lasers and LPKF manufacture the systems. These long wavelength fiber lasers are very high brightness, single mode, and that means highly focusable lasers. So for these polymer applications, where these are very big spots in laser terms, so we can use very long focal length lenses or even collimated beams, so to reduce line of sight access is really not a problem. Tooling and other components that sometimes get in the way are really not a problem with long focal length lenses. And the 120 watt power level, this is a unique fiber laser product that's the only laser of this type available on the market with the very high brightness, high average power lasers. And to go back to Josh's discussion on this particular slide, we've shown welding up to 21 different layers of 0.1 millimeter thick LDPE. One of the reasons I did this was because it actually shows the outline of the weld volume very nicely, and it shows that it obeys the classical Beer-Lambert absorption law as expected from first principles. And it is actually more of a recognizably of a welding process to those of you that are familiar with metal welding, it's similar mechanism in that you're melting a complete pool of material and moving that through the material. But as Josh rightly says, a lot of the absorption occurs at the interfaces because every optical surface has 2 to 3% absorption or thereabouts, so you do get enhanced absorption at the interfaces. So that's an interesting example, and it opens up a number of possibilities with using multiple sheets, incorporating, encapsulating different materials within these different layers. Lots of interesting developments we feel are going to be coming along. So move on to the next one, please. Okay, this shows some of the similar micro-welding that we did here with our lasers, and sub-100 micron features are fairly readily achievable. We're seeing 52 micron, a couple of thousandths of an inch weld features. So that's why the microfluidics guys are getting fairly interested in this technology. There's no other technique available for melting polymers in such a controllable manner. When I say controllable, I mean controllable both temporally and spatially. You can adjust the amount, the length of the pulse, and the amount of heat going in there down to microjoules and perhaps even nanojoules. And so you can not only control the amount, but you can control exactly where that heat is placed. So there's no other technique that allows you to control heating of clear polymers in this way available currently. Ultrasonics, RF, none of these other techniques have this controllability of the process. And that's why we feel that sometimes we're able to tweak the rules a bit with regards to material compatibility. So move on to the next slide, please. Again, on the right-hand side, we have a flexible polymer, sheet flexible polymer. We're seeing quite a lot of applications in medical devices. In this particular translucent polymer, we're actually you can actually outline the weld very clearly. Because of the obviously a change in the crystallinity of the polymers during the welding process, so the weld is outlined very nicely. And on the left we have a rigid polycarbonate type polymer, which is very much easier to join. You don't need a glass plate or a transmission. Because of the rigidity of the polymers, you can hold them together nicely and produce a nice butt weld. And we have a couple of these applications now for butt welding type applications. Again, as Josh said earlier, that part of the reason that we're able to produce these butt welds is because of the absorption at the interfaces. And is that the end of my slides? I think so. Is it, Josh? Okay, yep, we're back to your slides now. But I just wanted to make the point that these are fiber lasers that have been built for some time now. They were actually initially developed for surgical applications, but we've known for some time that there are these commercial applications for polymer joining out there. So these are not completely brand new lasers. This is simply a modification of the current fiber laser technology, and they're commercially available off the shelf and relatively well tried and tested fiber laser designs. These are not research lasers, and although due to the longer wavelength they're slightly more expensive than the conventional infrared laser, these lasers are very competitively priced with infrared lasers, perhaps 50% more costly, but again nothing like the costs of some of the more exotic lasers that are used in industry, such as the short pulse lasers, picosecond and femtosecond lasers. We're talking a small fraction of the price of those exotic lasers. So that's really all I think I need to say on the laser side. Josh, if we can go back to you.
Thanks, Tony. I appreciate that. And kind of along the lines,
okay,
sorry about that. Yeah, oh, sorry. Okay, I think we got it. So Tony, you were talking a little bit about butt welds, and so we actually got a couple of questions in regards to tolerances, gapping, and butt welds. So I'll cover this slide in a minute, but I'm going to let Shane review those questions, and then Tony, you and I can kind of handle them together.
Hey guys, so we've had a ton of questions coming in so far, and we'll get to all of them. Since we just covered applications and these types of butt joint welds, I wanted to bring up a couple that were relevant. Guys, Larry says he's interested in welding 2 clear flat parts, fairly thin, butt joints, and edge to edge. So he wants to know, what is the best way to do this?
Well, so Larry,
are they rigid polymers or flexible polymers?
I'm not sure if he mentioned that yet. So Larry, if you don't mind throwing that in, if they're rigid or flexible polymers, that'd be helpful.
I mean, obviously, if they're rigid, it's much easier to press them together to make the butt joint. I'm guessing you were going to say the same, Josh.
Yeah. So I mean, Tony has been playing with butt joints. We've told him for the longest time we were having an issue with, we'd have requests for butt joints with regular through transmission laser welding all the time, and we just said we can't do them. But with this, with transparent, with the 2 micron technology, we can. And so the reasons why we are able to do this is, one, as Tony was saying, it doesn't require, but it's much easier with rigid plastics. And that's because, recall, we need to maintain contact between the 2 pieces. So in order to do that, if we can press them together effectively, then we can get nice contact between the 2 parts. So rigid's naturally going to be easier to do that with from regards to a fixed train standpoint. Secondly, because the laser is passing through and volumetrically heating both parts, as you can see here on this butt joint, we're getting melt throughout the whole piece, whereas with regular through transmission laser welding, you'd only be seeing melt from one side, so we'd have to bring the laser in at a funny angle, and it just wouldn't work. But because of the way that the plastic's volumetrically heated and then pressed together, it works almost more like a hot plate weld or a IR weld. So in this instance, butt joints, although they can still be tricky, are very much possible.
Thanks, guys. And then it turns out Larry's application was rigid, so I think we got that covered. One more on the topic, Josh and Tony. Now, Jeff says wants to have a comment on interface gap tolerances for lap and butt joint configurations. So, Josh?
Yeah, Tony, you might have more specifics on this, but let me just say really quick, as far as typically you want to try to have the parts fit together as best as possible. So if not, then we're going to be clamping them anyways, so hopefully that'll overcome the gaps. In most laser welding applications, we like to keep gaps under 0.25 micron, and then 0.25 millimeter, and then once they are clamped, we like to see it around maybe 0.05. Anything more than that, it can be difficult. That being said, Tony, I know we have experience because of the volumetric heating. We tend to kind of get more of the plastics tend to swell together more, and because of that, we can actually overcome more gaps. What's your thought on that?
Yes and no. I mean, it is a laser welding process, so as with any other laser process, the tolerances have to be much tighter because you're using a much smaller heat source. And so yes, the better the tolerance, the easier it is to weld. And but like you say, if there is a little bit of a gap there, you know, a few thou of a gap, it can sometimes be taken up during the welding process by clamping. But it's always better to aim for as high a tolerance and as little gap as possible.
Yeah, so I hope that answers your question. So basically, try to get your parts to fit together as good as best you can. Clamping will hopefully overcome the rest of it, and then the laser welding process, although dependent on the plastic, can be finicky sometimes. We have seen some good results overcoming gaps. So
yeah, it depends again whether it's hard or soft. I mean, if it's soft, it's going to squeeze together. But we have seen issues where we're doing a butt joint in a flexible, and of course, if you squeeze it together too hard, it collapses, and you do get a lot of bulging. Having said that, we haven't mentioned yet, have we, Josh? In some circumstances, it may be appropriate to use a transmissive cover plate. You showed the nice example where you were using, was it a PMMA, an acrylic cover plate or a PC cover plate, and if you're clamping down through a transmissive cover plate, it is indeed possible to produce a joint with no expansion and no bulging on the top. But sometimes that bulge isn't necessarily a bad thing if it is indeed filling a joint gap. So very much material dependent. I'm sure, like us, Josh, the more welds, the more you do, the more you learn about it, and the more you appreciate the vast differences between the different types, the huge numbers of different types of polymers that are being used. It's not like metals where you can typically identify the properties of metal depending on which group they're in. With the polymers, as I think you said the same, Josh, even within a very apparently similar looking polymer, there'll be something in there that will stop it welding. So there are pitfalls out there that need to be looked at, and the answer is always, well, yeah, you've got to try it out. There's no theoretical model that's going to tell you whether it's going to work or not.
Yeah, absolutely agreed, Tony. And also the technology is new, so we're learning stuff every day, so we appreciate when you guys send us applications. We've worked closely with IPG out of their lab in Santa Clara. We also have the technology in our lab in Erlangen. So there's a lot of possibilities for getting samples tested and tried out. Wanted to jump back real quick. This last slide, just to cover beam spot size. Fiber lasers have the capability of getting their beam spots very, very small, under 100 micron, but we can bring them up, pull them out of focal depth, and we can bring them up to 3 millimeters. So we have a wide range of what we're capable of doing as far as the width of the seams you're looking to create. Again, Tony touched slightly on clamping, so we can do this a couple different ways. One is where we're using a glass clamp plate. Typically, we like to try to steer clear of acrylic with the 2 micron welding. We can use acrylic for regular through transmission laser welding. However, acrylic, it is a PMMA. It is a polymer, technically, so we have sometimes seen a good absorption of the laser into this. So we typically like to use a glass plate, borosilicate glass, to clamp with. And then obviously you just need support along the bottom. Another option is to use metal tooling, so we're just supporting or clamping the joint from either side as close as we can get to it. Tony mentioned an issue sometimes what you'll see, and again, this is entirely dependent on the type of plastic. There's an issue where because of the volumetric heating, you might get a small swell on this upper layer if you're not applying clamp force there. That being said, it's completely material dependent. We've seen results both ways. Sometimes you don't see it at all, and sometimes you do. So again, it just goes back to us testing the parts for you. Tony, you've kind of covered fiber lasers pretty well so far. The big thing that this slide was to indicate was the difference between a fiber laser and a regular fiber delivered diode laser. So again, Tony, if you want to take it away and touch on this, go for it.
Yeah, I mean, fiber lasers have pretty much revolutionized the laser industry for metal welding and cutting. Development of telecom technology in the late 90s, there were only a very small number of companies that were able to scale that technology up to industrial power levels. And interestingly enough, the first fiber laser wavelengths were in this mid-infrared regime, in the 1540 nanometer regime. Having said that, the majority of industrial fiber lasers out now there are in the shorter wavelength 1070 nanometer regime, because it's easier, even easier to build a high-power fiber laser at that wavelength using ytterbium as the dopant rather than the erbium 1540 wavelength and the thulium 1940 wavelengths that we're talking about here. But yes, the laser beam is actually generated within the fiber itself. The resonator is created by forming 2 mirrors actually in the glass itself, by writing fiber brag gratings actually into the fiber, and then the fiber is clad with the and the pump diodes are connected into the fiber and totally hermetically sealed. So no free space optics at all, and hence no possibility for contamination. very much the new technology within the laser industry, and this is simply an extension of that into new application areas. Changing the wavelength is simply using a different rare earth dopant in the fiber. I mean, clearly that's not done lightly. That's quite a significant change, but we've now been making these fiber lasers for a long time. That has also a number of implications with regard to reliability and with regard to ease of machine construction. You can isolate the laser source completely from the workpiece. So that's probably enough on fiber lasers, other than the fact that these are the highest, most highly focusable laser sources around. There are some shorter wavelength diode lasers, but you have real limitations in terms of efficiency, in terms of power availability, and in terms of the focusability of these sources. I see the analogy as simply using a sharp pencil to a blunt pencil. You can easily make a sharp pencil blunt, but you can't always make a blunt pencil sharp. So having a sharp point to start off with is always a better way to use the laser beam. That's probably enough on the fiber lasers, Josh.
Thanks, Tony. And just to clarify something, you see here 0.25. This is actually incorrect. It's, like Tony mentioned on the slide prior to this, it's actually closer to it's under 100 microns, so much smaller than this. We'll correct that in the slides when we send them out. Like Tony said, LPKF, we use IPG lasers in our systems, which that's what we're going to talk about next, is the equipment. That'll wrap up the presentation before we get into questions. But we do use IPG lasers. We are using fiber lasers, and so we agree with Tony. There are diode lasers out there that can handle these wavelengths, but we feel that the fiber lasers have the greater amount of advantages to them. So real quick, we're just going to cover the systems. The beauty of moving from regular through transmission laser welding to laser welding of transparent plastics is that it's a very simple process. We actually can use all of the same equipment that we have currently, and all we're doing is swapping out the laser source. There's a few differences, obviously, in the process, the way that the part's clamped and handled, but other than that, the systems themselves, the control mechanisms, and all the safety involved, it's all the same. So it's a very simple process for us to move from our current systems to a system that can weld clear-to-clear polymers. LPKF does offer fully integrated systems for inline automation. These can be put on dial tables or linear conveyors, and then also standalone units for lab use, as you can see here, or we can upgrade and start adding rotary tables for hybrid lab use in production. And like I mentioned before, it is Cleanroom compliant. These are actually pictures of the clean room that we have at our lab in Germany. It's a Class 5 rated clean room, and you can see we have two lasers in there, but this is the main laser we're using. This one over here is actually for radial welds, what you were looking at for welding catheters or tubes. But again, clean room compliant, so for all you medical device manufacturers, again, this is a great option in that regards. So that brings us to the end of it. Shane is now going to kind of take it back over, and he'll start reviewing your questions, and then Tony and I will kind of handle those in turn.
Thanks, Josh. Good job today, Tony and Josh. So we've got a bunch of questions, and we've got maybe 10 to 15 minutes left. So I wanted to mention that if we don't cover your question on air today, we will follow up with you, and we'll cover it then. We've been getting a ton of questions a lot of different ways. I've gotten some by email. I've gotten some in the chats. So we'll get to what we can. Now, I want to bring up something that Charles mentioned a while back. He wants to know, what is the maximum thickness that laser welding can go?
It kind of depends. Typically, we like to see thicknesses around, like you've seen the foils were down to 150 micron, but we like to see thicknesses of 3 millimeters or less. That being said, material dependent, we've welded much thicker. Tony, what's your experience with
Yeah,
average
I
thickness.
pretty much agree with you there. Getting up to 1/4 inch is generally getting a bit tricky because you're welding quite a large volume of material. If you are getting volumetric absorption, again, the volumetric absorption depends on the material. But yeah, 4 millimeters, 1/4 inch is getting towards the maximum, other than in some extreme circumstances.
Yep. Okay.
All right, thanks, guys. I wanted to mention something from Torben. Now, he has a really good question. He says, how do you avoid heating up the surface when you're not using a glass plate as a clamping tool?
I'm assuming if you're talking about heating up the surface using, well, let me step back. You're going to get volumetric heating throughout the whole part. So as the laser strikes any part of the plastic, you're going to get some heating there. Like we mentioned earlier, let me slide back to this slide here. You will be getting heating throughout the entire part. So you will see heat at the surface, and in some cases we've even seen bubbling take place at the surface. It's just dependent. That's why we do use glass plates, though, because they won't tend to absorb the laser and they won't adhere to the plastic if that does happen.
Yeah, I mean, the glass plate sometimes does suck some of the heat away, but my question is, why is it such a problem? You know, it's a weld.
Yeah, good point. So I mean, you have to keep in mind that we are volumetrically heating both pieces of plastic. So as we mentioned on the last question as well, if it's a thick piece of plastic, you're passing energy through the whole part, and so that's something to keep in mind. Goes back to even our joint models here. Lap joints are quite simple, but as you start getting too thick, then you're going to have volumetric heating through the whole part. There will be a point in time where you may not pass enough laser energy through to that bottom piece if you're too thick. Another consideration to look into would be if you do have a wall like this underneath your joint, you have to be careful that we're not applying too much energy into the wall. You might end up seeing deformation. So we've welded some parts that look exactly like this with this joint, and they look just fine. But we've also seen deformation in other parts. So it's material dependent.
Yeah, I think the one thing we haven't mentioned, Josh, is that it's always very important to design for the process. You know, you do that with every other welding process, and you design for this process. And if surface heating is a problem, then you design the part such that it is no longer a problem. But I think because people tend to be focused on the through transmission laser welding, there's this assumption that the heating is only going to occur at the joint. And if the weld is done properly, if the part is designed properly, if the tooling is done properly, it's really not an issue. It's like how most welds are done. The through transmission is the exception rather, and this is more of the rule. So there's a bit of a mindset that needs to be changed, perhaps.
Couldn't have said it better myself, Tony. So I actually got a few questions by email, of all places, and I'm going to bring one up from Christopher. He says, can you laser weld a clear part to a white part or a black part to a white part with this process? He mentions that both parts are similar plastics.
So when you start jumping into white plastic, it gets a little tricky. White plastic typically contains titanium dioxide pigmentations, and this tends to reflect laser radiation. We are curious to experiment with this wavelength of laser as far as how the white's going to interact, although from what I've heard is that it has a similar interaction. So white can be difficult, although there are new pigments on the market that don't contain titanium dioxide, but we don't have a whole lot of experience with them yet. So it is possible, but it does add a slight difficulty to it. As far as welding to black, if you wanted to go through clear to black, we've done that. So essentially what you're talking about at that point is a regular through transmission laser weld, but if you used a high wavelength laser, how would that change? At that point, you're almost asking yourself then why even use the high wavelength laser. So Tony, I don't know if you have any experience with.
Yeah, no, I'd agree with you completely on that. The titanium dioxide, yeah, you're right. There's some reflection. There's quite a lot of scattering goes on with the titanium dioxide. So yeah, you're right. It's sometimes difficult to get the absorption that you need. But again, it depends on the materials, it depends on the joints, it depends on the pigmentation, and really there's only one answer for that, and that's doing trials. The nice thing about doing the trials is it's remarkably easy to judge whether there's enough absorption and whether there's enough material compatibility to produce a joint. But as we've said, this industry is still relatively young, and we have to build up an empirical database. At this point, there's some low-hanging fruit, and there are still some questions to be answered.
Okay, thanks, Tony. So we are going to just take a couple more questions, and if your question doesn't get answered, like I mentioned, we are going to follow up with you via email, and you'll get your question taken care of then. So I just got a question, Josh, and earlier in the presentation you were talking about the Goldilocks area, and I got a question from Thomas about that. So he says you were talking about this Goldilocks area, which was the 1500 to 2000 nanometers, where the PC absorbs the laser appropriately. He says, is it a coincidence that all polymers absorb in that area? Is it the CC bond which is vibrated?
Tony, you might have to take that one. You're getting a little outside of my technical realm. I'm not a polymer expert. But the pattern, I can say this, the pattern, although what you're looking at on the screen right now is a polycarbonate, the pattern stays relatively similar for all thermoplastics. As far as the bond, Tony, are you familiar?
Yeah, there's some evidence that it's the third harmonic of the carbon-carbon bond that is generating some of this absorption. I think what I find interesting is, and you showed that absorption peak, I think there's actually a lot of integration and scattering going on, and I know some people have looked at producing a particular wavelength for a particular polymer. Our view, I think what we're saying, Josh, is that at this 1940 nanometer wavelength, there's enough absorption in a wide range of commercial polymers, or there's enough acceptable, usable absorption in a wide range of polymers to make the process valid. Further down the line, it might be necessary, particularly for thin films, to use a different wavelength in a polymer to produce a joint. But as I say, there's a lot of low-hanging fruit and readily accessible applications at the 1940 nanometer wavelength, which picks up. I say it's largely, we think it's largely the third harmonic of the carbon-carbon bond, but there's almost certainly some other vibrations going on there that we're picking up.
Thanks, Tony. That is exactly why we have a doctor on the line today.
I was going to say the same exact thing. So we'll do one more question on air today. It comes from Ken. He wants to know, what is the workpiece carrier made of? Is there any reflected energy off of it?
Yeah, obviously you'll get some reflection off of the workpiece carrier. Again, it likely won't be an issue because most of it will either scatter or just reflect back into the plastic. And the amount that does reflect back in would be relatively minimal. We do typically use aluminum-based nests, so with aluminum you will see some reflection, but unless it's highly polished, you're probably not going to see a whole lot. So again, most of it will scatter and just dissipate naturally. Tony, if you care to handle that one on your end?
No, I'd go along with you on that. I mean, either stainless because of the low thermal conductivity and aluminium because of the high thermal conductivity. But aluminium's a lot easier to make anything out of, so typically it's aluminium by default.
Yep. One thing I wanted to mention too before we jumped off, Shane's going to kind of handle our sign off here, but I did want to throw out, we talked about it a few times, but we didn't ever specifically mention it. The lasers that Tony is talking about, his fiber lasers, the terbium lasers, are typically about 1940 nanometers. That's the range that, like Tony said, we found is the most effective for the majority of thermoplastics. And so as far as from a commercialization of this technology, that's the wavelength that is kind of, as of yet, creating the standard. So just so you know, although I mentioned anything above 1500 nanometers technically applies to the technology we're speaking of today. If we start running trials on parts for you, or if we're just talking about this technology Outside of that, we're typically going to be talking about 1940 nanometer wavelength lasers.
Nicely put, Josh.
All right, thanks everyone. For everyone asking, we will send a copy of the presentation, a recording, as well as its slides. We'll probably be sending that out tomorrow. As I said, we'll follow up with all your questions. And I just wanted to give a big thanks for everyone attending today. If you have any further questions, go ahead and email Josh, jbrown@lpkfusa.com. Once again, thanks everyone for attending. And I'd also like to thank Josh for coming on the line, and a special thank you to Dr. Tony Holt. Have a good Thursday, everyone.
Thank you.
Thank you very much, everybody.